Hi, today I'm going to work through a optimization problem involving a box and volumes. It's one of the more done problems out there. Another one is a blimp problem, which I might get to. But for this problem, we're presented with a piece of paper, and this will be 30 by 16, could be anything, inches, feet, most likely inches. And the question is, if we were to make a box that folds up like this, what maximum volume can we achieve by cutting squares on the corners like this? So these squares will be cut off. So the paper will kind of look like a cross stitch. And by cutting those off, we can fold up different flaps and they'll fold in and we'll make a box. So the question is, how long does this side length need to be? We'll say X. And all these will be X because they're squares. At what size, when we cut off X, can we fold up the largest box? Well, first of all, we need to make a connection between what we know and what we want. And what we know is that we know the equation for volume. That's base times height times width. And at this point, we do know what the bases and heights would be. The base could essentially be this area right here, from this part we cut off to this part we cut off. Now, to see what that is, we have to notice that we're taking 30 and we're subtracting 2x, this x, and this x. So let's say volume equals 30 minus 2x. Okay, now what are we going to multiply this by? Well, we're going to multiply it by the width, or the height. Well, we can choose width. And we'll notice we'll be doing the same thing this way. We will be laying it back, and this length right here, right there, will be 16 minus 2x, because we're cutting off 2 x's right here. So we'll multiply this by 16 minus 2x. And now we need the height. Well, if we set up the box, this height will just be either one of these parts folded up. When we fold that up, we see this just as height x, because this will be folded up. So we'll multiply all this by x. So this equation, we'll find out the volume of the box we make. Now when we multiply this out, we get 4x cubed minus 92x squared plus 480x. So this is what we get when we FOIL it all out. And now, what we need to do in order to hunt for critical points and find maximum is take the derivative of this, and that'll be pretty simple. It's just using the power rules. So we'll say v prime equals 12x minus 184x squared plus 480. So now we have the derivative, and what we see is this does actually factor. If we pull a 4 out, we will get 4x, no, this will become x minus 12 times 3x minus 10. Okay, so now we're up to a farther point. And what we need to look at now is, what can the maximum and minimum be for our data? What we notice is, if we cut this by just 8, so if this goes out to 8, and we cut it that far, that becomes x. If we fold that, we won't get a box. So we say the maximum we can fold this is 8. So we'll say the maximum is 8. And the minimum we could cut that would also leave us without a box is 0. It's because if we don't cut anything, this will fold in, which will cut this, so we can't fold that in. So 0. So the minimum we can cut is 0, and the maximum we can cut is halfway, because these two will cut and meet, and we won't have a big box. So if we get any maximum or minimum not inside of that range, we can pretty much just throw them out. So now that we have our derivative, we can hunt for maximums by solving for x. So x can be 12, which is outside of our range, so that doesn't matter. Or x could be plus 10 over 3, 10/3. That is a maximum. And that does fit in here. That's 3.33 repeating. So what we found out is if we cut x to be 3.33 units this way and that way, we can make the largest box with that size paper. Okay, thank you for watching.